Most early-stage startups monitor system health the same way, by printing simple text to a terminal. As long as the console is quiet, everything seems fine. That quiet holds until production inevitably breaks at 2 in the morning, and the team scrambles to figure out what went wrong. Instantly, a wave of unanswerable questions hits. You try to isolate exactly which inbound web request triggered the failure. Then you have to figure out which specific client or tenant was actively using the application when it crashed. You dig into the infrastructure, trying to determine which specific background worker thread was processing the faulty data. And ultimately, you need to know if this was a one-off anomaly or the beginning of a total system failure. Operating without dedicated architectural observability leaves backend engineers completely blind. During a critical outage, debugging is reduced to pure guesswork. The root of this blindness comes from treating raw, printed text logs as actual system visibility. This comparison shows the difference. On the left, an unstructured text string like "something failed" might make sense to the developer who wrote it, but it becomes entirely unsearchable at scale. On the right is structured data. Log data must be formatted explicitly for machines to parse, query, and filter. A useful log entry requires foundational data points. It needs a specific request ID and a tenant ID to anchor the event to a specific user. It also requires precise metadata, the exact route, the worker name, latency in milliseconds, and the specific error code. Standardizing these logs makes it possible to filter through millions of events. Humans should understand logs instantly, but machines have to parse them first. Structured logs work well for a simple, monolithic application, but modern architectures distribute logic across dozens of distinct microservices. A single action hits the API gateway, instantly fracturing into asynchronous streams. Entering a message queue, the original context vanishes. If a worker crashes later, you cannot trace the failure back to the specific API call. Without a connecting thread, these systems operate as isolated black boxes. As architectural complexity scales, traditional logging fails because it lacks a unified, trackable narrative across different servers. The engineering solution to this distributed black box problem is context propagation, driven by a correlation ID. This begins the instant a request hits the ingress point. The gateway generates a unique identifier, permanently attaching it to the API context. As data moves, this identical ID is forwarded seamlessly into message queues. Background workers utilize it while processing. Finally, the same ID is recorded in database tables and outbound webhooks. By passing this ID downstream, a single database search query can now reconstruct the entire event timeline across every service. Context propagation links API, queue, worker, and database together, transforming isolated server events into a fully transparent request lifecycle. Scaling a production environment introduces a secondary crisis: severe alert fatigue and monitoring noise. When a core service goes down, an engineering team can receive hundreds of automated alerts in minutes, all stemming from a single root-level issue. To manage this, the platform groups errors intelligently using distinct error fingerprints. Instead of treating every stack trace as unique, errors are consolidated based on the API route, worker type, and deployment version. This intelligent sorting actively prevents alert spam. 500 identical stack traces do not represent 500 separate incidents. They are a single incident, and grouping them is the only way to separate critical signal from operational noise. There is a common assumption that observability platforms exist exclusively to track technical server crashes and 500-level errors. This dashboard demonstrates a different approach. Core business logic failures require the exact same engineering rigor as a database crash. This includes constant monitoring of specific business-critical events, like automated billing transitions and subscription states. It also means tracking scoped permission denials and monitoring how those access issues directly impact the user experience. Tracking these specific non-technical events provides a genuinely holistic view of overall system health. An unseen business failure is exactly as detrimental to a startup as a technical crash. Business event observability is a non-negotiable architectural requirement. In a distributed system, catastrophic outages rarely happen instantly. They build up slowly over time. Automated system alerts exist to detect subtle anomalies long before they escalate into full downtime. This graph shows the first early warning sign, an uncharacteristic spike in queue retries. The second critical sign is a creeping increase in API endpoint latency. The third metric is rapid, unchecked growth of a dead letter queue, catching jobs that failed entirely. By monitoring these specific thresholds, engineering teams can shift from reactive firefighting to proactive anomaly interception. The most dangerous belief in early-stage engineering is that raw text logs are sufficient for a scaling application. True debuggability at scale requires 4 non-negotiable pillars for your architecture: distributed tracing, context correlation, precise metrics, and strictly structured events. Building around these pillars creates a foundation for managing production environments with clear visibility rather than guesswork. With observability in place, the next step is safely shipping code. That means establishing zero downtime deployments, robust rollback strategies, and strict container management. I built these exact observability principles directly into my own platform. You can see how they operate by visiting app.saasplatform.app. Follow along for the next installment on deployment architecture.